Welcome back, applied calculus students. We're doing applications, and this is section 4.4, getting ready to do number 2. Again, we're looking at maximums and minimums. So first derivative analysis. The total daily cost in dollars of producing X mountain bikes is given by this cost function. Find the marginal cost function and the average cost function. Graph these functions on the same coordinate axes. So there is something in this for you economics fans, looking and comparing average cost and the marginal cost. So we're going to do part A. You've got your cost function was given, and I rearranged it to put it in standard form. You don't have to. The marginal cost, remember, is the derivative of the cost function. So use proper notation. C prime of x equals, bring the 2 in front, multiply, get a plus 5, derivative of 1,000 goes away. And this is the cost. So this marginal cost is the margin of costing, producing one more bike. So the cost of producing one more bike. So if you plug it in at a certain production level, you'll find out how much it costs to go from that production level to adding another bike. Now, average cost is, remember, you take the cost function and divide by x, and the average cost is just the average cost it is costing the company to make the bikes. The price per, or sorry, not price, I can't say that word, cost per bike. Now what we're going to do is graph these. So I gave you the wrong one. I gave you the window. So 0 to 150 by 50, 0 to 50 by 10, and we're graphing both of these. All right, so I did 0 to 150 by 50s, 0 to 50 by 10s. This is bikes, this is dollars. So if you do this correctly, you can pause this and see if yours comes out. Your marginal cost is linear, so it should have been a line. Now your average cost is divided by x, so it's giving this curve here. And we are done with part A, and we'll look at part B. What's part B say? Use calculus to find the minimum average cost. All right, so we're looking for minimum average cost. Minimum says take the derivative of that function. So looking at the derivative of the average cost, well, remember what your average cost function looks like this. And I need to take the derivative. You can do quotient rule, but in this case, I think I'm going to use a simplification of this average cost, divide each one by x, and then I get 0.1x plus 5 plus 1,000 x to the negative 1. Or you can use quotient rule. You'll get the same, what's the word I'm looking for? Critical number. So we're looking at the derivative of this, and the derivative of that gives you 0.1 plus that's 0, and then negative 1,000 x to the negative 2 power. Rewrite that. We did this in the last problem. Bring that to this side. Cross multiply. So 0.1x squared equals 1,000. But don't square root here. Divide. You want to get your x squared alone before you square root. Warning. Make sure you do that. And x squared equals 10,000. When you do that division, you get plus or minus, and we talked about looking at x as a positive number. And then, what am I looking for? Minimum average cost. So put that back into your average cost function, and you get 25. So if you can go way back here, put it in here, or you can put it into the simplified one, whichever you feel most comfortable. But you should get 25. And I'm going to conclude at a production level of 100 bikes. The average cost is at a minimum of $25 per bike. Note that this ordered pair, 125, is the intersection of marginal cost and average cost. Right here. This is the 100, 25. And there's a whole, in economics, they talk about, and I'm not going to explain this to you. You can look it up if you're in, for you economics nerds. You can go look this up. This point is referred to as the minimum efficient scale or efficient scale of production. It is the lowest point where the company can produce such that its long run average costs are minimized. All right, I'll be back for the last one.